So let's talk about power distribution in our series DC circuit. So when we apply any power to our circuit, the power applied is going to equal the power dissipated or absorbed by the circuit. So the power applied by the supply has to equal that dissipated by all of the resistive elements. So we're going to practice actually calculating that power absorbed or power delivered. So the power delivered to the circuit by the source has to be absorbed by the individual resistors in series, and we're going to see that it indeed does. So let's work through this problem and calculate the power delivered to this entire circuit and the power absorbed by each of those resistors. So in this circuit, we're going to start working through this the same way we have all of our others. So our total resistance we're going to find first, and we have a 1K ohm, a 3K ohm, and a 2K ohm resistor. So that's a total of 6 kilo ohms of resistance. And then we know that our voltage source is 36 volts. That was given. So the source current that is supplied to the circuit would be E over RT, which is 36 volts over 6 kilo ohms. So we must have 6 milliamps of current through our circuit. So I'm just going to make a note of that, 6 milliamps. And that's the current through each of our resistors as well. So when we're finding power, remember from chapter 4 that power is equal to voltage times current. So if we're talking about the power delivered to our circuit, then we're actually talking about E times I sub S, or the source current delivered by the source itself. So E in this case was 36 volts, and I sub S is 6 milliamps. So that means we have 216 milliwatts of power that we are delivering to our circuit. Now let's look at the power absorbed by each of our resistors. And in order to do that, let's find our voltage drops. So V1 is the current through R1 times R1. So I1 is 6 milliamps. Why? Because R1 is in series with the source, so it's going to have the same current as the source is supplying. So 6 milliamps times 1K ohm of resistance means we see a voltage drop of 6 volts there. V2 is going to be I2R2, where we have 6 milliamps and 3K ohms of resistance, which should be about 18 volts there. And then V3 is going to be I3 times R3, or 6 milliamps times 2 kilo ohms, or 12 volts. So our 6, 18, and 12 all add up to our 36 volts, which checks out. But what we're really interested now is the power absorbed by each resistor. Okay, actually I'm going to name it a little differently. I'm going to call it P1 absorbed, okay, because we're talking about the power delivered or absorbed by our resistor there. So that's going to be V1 times I1. So the voltage drop across R1 times the current through R1 gives us the power absorbed by that resistor. So that's 6 volts times our 6 milliamps. So we see about 36 milliwatts there. P2 is the voltage drop across R2 times the current through R2. So we've got our 6 milliamps there times 18 volts. So that's about 108 milliwatts. And then P3 is V3I3, where we've got our 6 milliamps this time times 12 volts, which should be 72 milliwatts. Now if we sum these, so 72 plus 108 plus 36, what do we get? We get 216 milliwatts total Okay, that's the total absorbed by all of our resistors. And notice that's exactly what our source is delivering. So in terms of power, the power delivered by our source has to equal the sum of the power absorbed by all of our resistors.